So some quick announcements about the course. Let me get my quick announcements. Announcements, OK, lots of announcements today because it's the first class back from the break. The most important thing is that you know is that the midterm 1 has been returned. So midterm 1 got returned. There is an announcement on CourseLink that has lots of important details. You should definitely read the announcement carefully. One important thing is what is the midterm out of? If you go to Gradescope, it will give you a number, and it'll say your grade is X. That is not your grade. So to figure out what your actual grade is, you need to do some interpretation, some math, if you will, and you need to figure out what is your grade out of, and then calculate it yourself. All the details are on CourseLink. So that is an important thing. Another important thing, if you didn't do so well on the midterm, don't worry, it was only midterm 1, and there's lots and lots of time to improve before midterm 2. There's a lot of resources in the course that people aren't using a lot right now, so like the Campus Wire forums, all the office hours we have, the Math Aid Center. If you want to do better on midterm 2, you have lots of time. I recommend you just put in as many hours as you can. One thing that some people kind of don't realize in their first year of university is that compared to high school, you're basically putting in way, way more work outside of lecture than in lecture. So in high school, you sort of do the entire class is mostly in the lecture and maybe a little bit of homework. But in university, it's the opposite. Most of the learning, most of the work is outside of class, and the lecture is sort of just like, I think it's kind of like a road trip. Like learning is like a road trip, and then the lecture is like when we look at the map, right? Most of the trip is you driving around, you know where you're going, and like a little bit of it is like figuring out what you're going to do for the next like hour. So in high school, it would be like 9 hours a week of lecture if you did a high school course in 12 weeks. In university, we give you 3 hours a week. And the other 6 hours a week are missing. You're supposed to do them yourself outside of lecture. And that's why there's so many resources, so many problems that are posted. It's to give you something to do to learn the material. So if you didn't do well on midterm 1, you still have another chance on midterm 2. And to help extra motivate you, this is extra motivation, I'm introducing something called the Midterm Improvement Motivation Plan. Excuse me. So here's how it works. If you improve on midterm 2, so you do better on midterm 2 than midterm 1, then your midterm 1 course, like the amount it counts on your grade goes down, and the amount midterm 2 counts goes up. So if you do better on midterm 2, I don't need the timer. OK, you go away. OK, so if you do better on midterm 2, then midterm 1 gets reduced from 20% to 15%, and midterm 2 goes up from 20% to 25%. So they go from being equal to midterm 2 is worth almost twice what midterm 1 is. And assuming you do better, this could only improve your grade. So if you don't do better, then your grade is the same as it would have been. If you do better, then your grade goes up. So I'm hoping this extra motivation will help people put in the hours and study for midterm 2. Any other questions or comments about midterm 1 or midterm 2? Yeah. Yeah. Yes, right. I will calculate it both ways, both the normal way and the improvement way, and I give you the better one. Yes. And this can only improve your grade, right? So it only gives you more weight on midterm 2 if you do better on midterm 2. If you do worse on midterm 2, then you just get the regular thing. It's like this never happened.
But I'm seeing that it says like 25% and then 18%, so like whichever is better.
Yes. So this program can only improve your grade. It will never ever make your grade worse. So if you want, you can just ignore this and pretend it's the regular thing, and then you get a slightly higher grade on your final grade, assuming you do better on midterm 2. Yeah. OK. Any other questions or comments? Midterm 1 or midterm 2? OK. So the other important announcements are about the feedback. So right before the break, I posted a feedback form, and I asked people what they were using in the course, what they would like to have changed in the course, what is working well in the course. The most overwhelming comments I got were the top 2, is that people really like the extra videos. They found those helpful. So out of all the options, not helpful to haven't tried it to most helpful, almost everybody picked the extra videos are very helpful. And people also said they want lectures to go slower. If you combine those 2 bullet points, how are we going to make lectures go slower? The way we're going to do it is I'm going to make more extra videos, and I'm going to try to do fewer examples more slowly in lecture. So fewer examples more slowly in lecture, and lots of examples posted as extra videos outside of lecture. So more examples move to extra videos. The other thing I'm going to try to do is a lot of times in math, it builds, right? So like we're doing a problem where the new thing is logarithms, but we're doing it with algebra that we did from the high school algebra quiz. And then there's a new thing at the beginning, and then there's a lot of algebra steps that are review from what we did before. So I will try to highlight what is the new thing more, because I think some people aren't seeing that a lot of the work we're doing is review from other things. It's normal to have to go do it in class, and I do them like quite quickly because that's not the new thing. So I'll try to highlight that better as well. The other thing that I think would help a lot is if you guys ask me more questions. So part of the way I choose how fast the lecture is going is by how many questions there are. If nobody asks any questions, then I'm just going to move on to the next thing, and then we end up going quite fast. Where if people stop and we ask questions, then it will naturally slow down, and I think that's great. So if you have questions, please ask them. I'm happy to go at the speed that is best for you. Whatever is left over, I will put in as extra videos. So don't feel like there's a certain amount we need to get to. I'll just move them to extra videos. The other comment I got quite a bit was that some students say the classroom is too loud. So I'm going to try to make an effort to tell people if it's too loud, I'll stop and I'll say I'll wait for people to quiet down. And I will particularly do this during questions. So if somebody asks me a question, I will make sure that everybody else is quiet. If you find people are annoying you, just ask me a question. Ask me a dumb question like, what is that written on the board over there? And then I will stop everybody and make sure everybody's quiet. Question here.
I know we had math test
Yeah.
that is due on Friday.
Yeah. So there'll be some due on Monday for this week, from like what we're doing today. That's right. Yeah. That's going to the reminders are make sure you watch the recorded lecture. So the very last day of class, we didn't have an in-person class. I recorded it. You have to watch that. And I moved the deadline to Monday. So there's going to be a whole bunch of things due on Monday. If you wait till Monday, it's going to seem like a lot to do in one day. It's because it's stuff from a long time ago. There was no homework after the midterm either. All of that stuff is due on Monday. You can definitely do like 90% of it right now, so there's no reason to not get a head start. So those are the reminders. Yeah, I have to press the send button. It'll be up tonight. Yeah. Okay, last but not least, just a reminder of all the course resources. So a lot of people in the feedback, they said they weren't using any of these resources. I want to make sure people know about them because they are, you're paying for it. Like the Math Learning Center, there's TAs that sit there and they get paid with your dollars. Same thing with the TA office hours. Those are your dollars. Campus Wire is also answered by me and the TAs. You can post there anytime, and it's free bonus marks. So I really encourage you to post questions there. If you have a homework question, even if you got the right answer and you're like not sure why it is the way it is, you should post. The other thing I've done is I have removed the time limit on all the homeworks. So the homework used to be 2 hours, but now it's as long as you want. It makes it easier for you to look up the answers, which is not good for your learning, but I hope it will also make it easier for you to get help. So if you take your homework and you want to go sit in the Math Learning Center and just do your homework there, that is a great way to make sure you know the answers. Some people said the hours weren't working for them, so we added another time. Tuesday and Thursday from 4 to 5, there's going to be Zoom office hours with the TAs. That's in addition to the 6:30 to 7:30 that already exists on all the other days of the week. And the other thing to remind you is the way the midterms and the finals work is I take problems from the homework and from lecture, and I repackage them, change the numbers, twist them a little bit, and put them on the exams. So you really should try to understand the problems deeply. That's the best way to do well on the midterm. A really good example is the midterm. One of the hardest questions on the midterm by how many people got it right was the problem with the table. There's a table, and it says, please find f of f, please find g inverse. And a lot of people got that wrong, even though on their study sheet, they had the identical problem that was on the homework. So on their homework, you had a problem just like that. There was a table, please find f of f, please find g of g. They copied down that problem exactly. They copied down the answers from the homework, but then they got it wrong on the exam. And I think it's because they were just like trying to get the right answer, but not thinking about how it works. So I really encourage you, try to understand the homework problems deeply. And if you need help, come get help. We're here to help you. Okay. Last but not least, the feedback form is still open. So if you haven't given me your feedback yet, I'm happy to take it now. You can post there anytime, and I will read it, and I try to take it seriously and improve the course. So let me know if there's anything else that you guys want. All right, yeah, another question. You cannot get the physical copy of the midterm because they're all in a big pile. Oh, I suppose, okay, if you want to come and look through the pile and find yours, then you can. But I don't want to spend time sorting them out. So if you really want the physical copy back, you can come get it. On Gradescope, you should be able to see a scan of it and see exactly what you did and how we graded it. Yeah, so I guess you can come get it if you want to look through the pile. OK. Yeah, any other questions or comments about the midterm or any of the stuff we're changing or anything else in the course? OK, so let's move on to what we're actually doing today. So we're starting with sequences. We're doing section 8.4, which is the graphical representation of a sequence. And if we're going to do the graphical representation of a sequence, we need a sequence to work with. And that was the example I gave you here. So Mr. Beast wants to give us $9,000, but he gets caught in this infinite loop of giving us more and more money every day. Of course, even though he's giving us more and more money every day, the amount of money is going down by quite a lot. So on the first day, he gave us $9,000. Very nice. We can like go buy a used car, I guess. On the second day, he gives us $900. What does he give us on the third, fourth, and fifth day? That was the question. And let's see what you guys said. On the third day, oh, I revealed the right answers. OK, that's fine. On the third day, he gave us $90. That's correct. And it even says in the question text, on the third day, it's $90. It's 10% of the $900. What other answers were popular? OK, I guess 0 and 1. No, those are wrong. $9, also quite popular for B4. And that is correct. So 10% of $90. On the fourth day, he gives us 10% of what was on the third day. That's $9. On the fifth day, he gives us 90 cents. 90 cents, 0.9. And that's because he gives us $9. Tax on $9 is 90 cents. OK. What other answers? I guess people, 0 and 1, people maybe ran out of time or something and are feeling lazy. OK. So that's the sequence, 9,999, 0.9, 0.09. It goes on forever. How are we going to represent this graphically? So this is the section, graphical representations of a sequence. There's two methods. Procedure 6 says method 1 and method 2. Method 2 is the more usual one. Plot the sequence of points n, comma, a, n. So let's see what that looks like in the notes. So what do I want? I want this, and then here. OK. OK. So plot the sequence of points n, comma, a, n. So n, comma, a, n. So for us, it's the sequence 1, 9,000. On the first day, he gave us $9,000. On the second day, he gave us $900. On the third day, he gave us $90. On the fourth day, he gave us $9, and so on. And this goes forever. So it's a sequence of points in the plane. You can draw them. Instead of drawing them by hand, I have them in Desmos. So that's what this looks like. And let me do a little something here. So here is the sequence of points. It's a little bit hard to see them. Let me change the scale a little bit. So I want the y-axis is going to go from, let's say, -$1 to $10,000. So this goes all the way up to $10,000. So you can see those blue dots. That's what we're doing. And the x-axis is going to go, those are the days. That's going to go from 0, say, to 6, the first 6 days. OK, so now we kind of see what's going on. On the first day, he gave us $9,000. On the second day, he gave us $900. On the third day, he gave us $90. Fourth day, $9, and so on. So it's a sequence of dots, and it moves to the right because we keep adding to the x-coordinate. The x-coordinate is what the number n is. Another way people often do this is they connect the dots. So let me go into settings here, and I'm going to tell Desmos, please connect the dots. So you check this thing. And now, same exact thing, but the dots are connected. And now you kind of see the pattern. It's going down, right? It's a function. It starts at 9,000, and it seems to be going down, 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 down. We actually know the formula for this. So let me go up here. Here's our Mr. Beast problem. The formula is actually known. The formula for what he gives us on day n. It turns out you can know what this is. And the reason is it's because it's a geometric sequence. So if you watch the extra, not the extra lecture, if you watch the lecture from Friday's class, you'll know about geometric sequences. And the formula for this geometric sequence is the first term, 9,000, times 1/10, that's the 10%, 1/10, to the power n minus 1. So the formula is this. Bn is this stuff. So another way you can see the sequence is to just plot this. So if you go into Desmos and you say, please plot the function, here it is, 9,000 times 0.1 to the power x minus 1, you can tell Desmos to plot it. let's do a slightly different color here, just so I can keep things straight. Let's do this one. Oh, let's just do a dotted line. No. Solid line. Let's pick the color purple. I like the color purple. OK. So I've plotted the function as a function of x. So Desmos is pretending the n value is x, and it's plugging in all the x values. And it's this nice smooth function. In fact, it's the exponential function we talked a lot about before. So the only difference between the exponential function and our sequence is that our sequence is just dots. 1, 2, 3, 4 are the n values, whereas the x values can be anything. OK, so we have a picture of our sequence. We have the dots. We got it filled in. We know everything. The question that was in Mathematize for you to answer is the amount of money that Mr. Beast gives you on day n is getting closer and closer to what? And you guys said 0. 84% of people said 0. It's getting closer and closer to 0. And you can clearly see that in this picture. It's getting closer to 0. The y values are getting closer to 0. OK. Any questions or comments? I'm going to present this in a different way in a second. So far, we've done method 2. In a second, I'm going to do method 1. Method 2 is like what you're used to. It's like a plot of x, y. Very simple stuff. Method 1, I think, is actually better, but is a little more unusual. That's why I did method 2 first. And this is a good time. If anything is unclear about the picture, this is a good time to stop me. Yeah? Yeah, I can put the workbook up. So far, what have I written in the workbook? Almost nothing. Yeah, there we go. OK, we have y, k, and f, so I can freeze this up there for you guys. Mr. Beast is not in the workbook. So what have we done in the workbook so far? So far, all I've written is this, these numbers. OK, but I want to show you guys method 1 for Mr. Beast. In a second, we're going to do the workbook exercise 144. Plot the numbers on a number line. So plot them on a number line. And that is what this would look like. So I want to show you what this looks like. Plot them on a number line. So here in Desmos, I'm going to make the numbers like this. So before it was 1, 9,000, and now you just have a line at 9,000. So the x value is 9,000, and the y value is just this vertical line. I've drawn this vertical line. This represents B1. And then on the second day, he gave us $900. That's this line over here. And the third day, he gave us $90. And on the fourth day, how many dollars did he give us? It was $9. And on the fifth day, how many dollars did he give us? It was 0.9. OK? So this is method 1. Just draw the points instead of using x and y. Just draw them all on the axis. And why is this nice? Because I want to show you something cool you can do. You can just zoom in forever and see where do the points bunch up. The points are bunching up. They're getting closer and closer to what number? I'm just hitting zoom in over and over again here. Zoom in, zoom in, zoom in. They're getting closer and closer. Like on some day, he gave us $0.009, but I can keep zooming in. This is the magic of the zoom button. You can zoom in forever, and it's just getting closer and closer to 0. And you can see that very clearly with this method. On the other method, you would have to move to the right. You have to go on the axis all the way to the right. But on this method, there's just one spot, and the points get closer and closer to that spot. And this is the idea of getting really, really close to something. This is called a limit. So we are seeing visually that the limit of the sequence is 0. Because if you zoom in forever, look at, I zoomed in so much, it's giving me scientific notation, and there are still infinitely many Mr. Beast dollar signs coming at me close to 0. OK, that's the idea of a limit, and that's the idea of method 1 of plotting everything on a number line. The other thing I want to say about this is it's not just that we're getting close to 0. Close is fine. We are getting close. But we're getting sort of, quote, arbitrarily close. What do I mean by arbitrarily close? I'm going to illustrate this. Let me zoom back out. Let's zoom back out to numbers we understand. To numbers we understand. There's 90. OK, there's 9,000. OK, there's all the numbers. So on day 1, he gave us oh, that's 900. OK, wait, let's get 9,000. OK, day 1, he gave us $9,000. I'm going to make a little zone here. And I'm going to make it around 0. So I'm going to make a little zone that looks like this. Let's make it 3. Here is my little zone. OK, you can't see my little zone. Let me make it bigger. $1,000. $1,000. OK, what have I done? So here is the point. Mr. Beast on the first day gave us $1,000. Let's pretend you're Mr. Beast's accountant. OK, you're doing all these transfers for him. And you are rich, so you don't care about any amount of money less than $1,000. If it's less than $1,000, you don't care. How do you illustrate this on the number line? that region of green, that green vertical stripe, is everything that is within $1,000 of 0. That is everything you don't care about. If you're a Mr. Beast accountant, everything in that green zone might as well be $0. Less than $1,000, it's not worth your time to work with it. So if that really was the case, Mr. Beast would send you his first day, $9,000, and on the second day, it's like, OK, $900, that's close enough to 0. We don't care anymore. Of course, real accountants care about things that are, and $900 is still a lot of money. So maybe the accountant actually only cares about things that are less than $100. So maybe it's that really thin green vertical stripe. Well, now Mr. Beast is going to give you money for 2 days, 9,900. But on the third day, you're within the green vertical stripe. OK? So no matter how small this green vertical stripe is, after a few days, it seems like we're always within the zone. What if we only care about numbers that are less than 0.00001? OK? That's like 1/1,000,000th of a cent. I'm a really greedy guy. I will never round down my money unless it is less than 0.001. Now you can't even see the green vertical stripe. But if I zoom in enough, let's keep zooming in. Zoom in forever. Zoom. I should get the sound of the hypnotoad to play while I do this. OK, where is it? There we go. Zoom in forever. I might have made it too small. Let's see. Are we ever going to find the green vertical stripe of 1/1,000,000th of a cent or whatever I put in? Come on. Oh, I think I see it. I'm starting to see it. So here it is. Look, there you go. There's the green vertical zone. And the sequence of numbers, even though it looked like it was nowhere near that, eventually it's entirely in this green vertical stripe. And this is the idea of arbitrarily close. No matter how thin the vertical stripe is, no matter how arbitrarily small I make it, eventually the sequence lives in the green vertical stripe. This is the idea of a limit. And we would say mathematically, in the Mr. Beast example, we would say the limit as n goes to infinity of bn equals 0, and we would say it's because no matter how small the, let's say it in words, green vertical stripe is. Stripe is around 0. So we think the limit is 0. We draw a stripe that is centered around 0 of some width. And no matter how small the width is, no matter how arbitrary we make that up, eventually, bn is within the stripe. OK. So this is the idea of a limit. I did it with this Mr. Beast example. We're going to use Mr. Beast again next class. So that's why I wanted to do him now. So OK, that's the words. And I want to do this. Those are the words. And here is the picture. And of course, the picture goes with this idea of zooming in forever. Any questions or comments about this is the big idea in the lecture today. If you only understand this big idea, that's a successful lecture. It's a subtle idea. Questions or comments about this one? Am I a big Mr. Beast fan? No, but I thought you guys would be. I don't know. If he gave me $9,000, I'd be happy. Yeah. Anybody else? OK. Let's move on. So we're going to move on to doing the example in the notes. And again, I think the Mr. Beast example, it's a little silly, but you will see next class, it will make perfect sense why I did the Mr. Beast example. So it's setting up something for next class that is very nice. But for today, we're going to do the boring example, which is exercise 144. So the rule an is n over n plus 1. Not as exciting as Mr. Beast, but we're going to do it nevertheless. Let's fill in the numbers. So here we're going to put in some numbers. OK. When n equals 1, so I'm going to make n equals 1, 2, 3. I'm going to put that on the bottom here. What is the number? N is 1, and the bottom is 1 plus 1. So it's 1 over 1 plus 1. That simplifies out to a half. So let me do it like this. I'm going to do a n, and then here is the simplified version. I'm writing it twice. When n equals 2, it's 2 over 1 plus 2. 2 over 1 plus 2 is 2/3. And when an equals 3, it's 3 over 1 plus 3, or 3/4. When n is 4, it's 4 over 1 plus 4, which is 4/5. And when n is 5, it's 5 over 1 plus 5, 5/6. So I think you see the pattern. It's always the number divided by the number of plus 1. A half, 2/3, 3/4, and so on. So that's the sequence. That's the sequence. What does it look like? That's on the next page. So here is, let's do method 2 first. Here's method 2. Here's the sequence. So this is a half, this is 2/3, this is 3/4, this is 4/5. And you can see in method 2, you plot the x values are 1, 2, 3, 4. You get these dots. You can connect the dots if you want. And to find out what is the eventual behavior, what is the limit, you have to look to the right. So you kind of like your eyeball. This is supposed to be your eyeball. You have to look over here, and you have to imagine looking that way, right? OK, you look that way. Oh, geez. OK, so you have to look. I guess you have to look this way. You have to look over there and see where does it go. Where does it go eventually? OK, that's method 2. In method 1, let me compare and contrast. In method 1, we plot all the numbers on a number line. So here is 1/2, 2/3, 3/4. They're already labeled for you. And you can see they get closer and closer to 1. And if you zoomed in, the point is that no matter how small of an area you draw around 1, if you zoom in, the numbers get closer and closer to 1. OK, let me stop. Are there any questions or comments? OK. So what does this look like on Desmos? Let's look. So this is the sequence. an is n over n plus 1. That's the sequence. So what do they look like? Of course, they're nowhere here. This is a stripe around 0. That's not where they're going. Let's zoom back out. Where are my points? There they are. You see all these orange lines. And they kind of accumulate. They accumulate near 1. So we think the limit is 1. Oh boy. Guys, something bad is happening. Look, there's 1. There's 1. And there's my orange lines are the numbers. And it looks like it doesn't work. It looks like it doesn't work. Because let's make L equal 1 here. L equals 1. And let's make my green stripe a little bit bigger. 0.001. OK, there we go. Look at that. There's the green vertical stripe at 1. And there's my sequence in orange. And it's getting close, but it's not inside the green vertical stripe. So that means the limit is not 1. Something is wrong. Something is wrong. Does anyone want to take a guess as to what is wrong here? Right? In the notes in the notebook, it looked like it was getting close to 1. They're trying to tell us clearly, this is a math word that means I don't want to explain. If someone says clearly, they're trying to trick you. I don't want to explain. That's what this means. So watch out if someone says clearly. Clearly, as n gets large, it gets closer and closer to 1. But what happened here? I did it in Desmos, and it's not getting closer and closer to 1. It gets close to 1, and then it stops. What could the problem be? Do you guys want a minute to think about it? I'll give everybody a minute to think about it. Talk to the people near you. Try to figure out there's something I did wrong somewhere. And if I fix it, it will go to the green zone. But I didn't do it right. So what is the thing that dumb Professor Nika did that was wrong? OK, 1 minute. Okay. Has anyone figured out what's wrong? Why is it not in the green zone? Anyone want to take a guess? So in the notes, it looks like it's getting really close, right? Why don't we have this problem in the notes? Yeah. Maybe n has to be switched. I think you're on the right track. You think the formula is wrong or something? Well, so OK, the actual formula is correct. So the formula here is n over n plus 1. That's in Desmos. And in the notes, it's also n over n plus 1, n over n plus 1. And the numbers are the right numbers, right? It's 1/2, 2/3, 3/4. Those are the right numbers. So in Desmos, it is doing all the right numbers. Like, way out here, maybe I have to keep going. 0.9. OK, I'll zoom out once. So there's 1/8. There's 1/2. 0.66 repeating. 0.75. So all the numbers are right. The formula is right. But there is something that is funny about n. There's something going on with the n. So you're right about that. There's something about the n that's not quite right. Let me scroll up on the screen. Maybe I'll bring it up here. Let's look at how come we don't have this problem why is it a problem in Desmos but not a problem in the notes? In the notes, it looks fine. It looks good. It's getting really close to 1. You can write the sentence clearly as n gets larger, it gets close to 1, and you're fine. Yeah? What about -1? You're saying when n equals -1? This? Yeah. OK, this is the distance. This is the absolute value of an minus 1. That is saying how far are you from 1? So this is the value 1. And we're talking about an minus 1 is this distance. 1/2 minus 1 is 1/2. The distance is 1/2, and then 1/3, and then 1/4. So in the notes, they're talking about the distance to the value 1. So you could do the same thing on Desmos. We would be talking about the distance from these orange lines to the line at y equals 1. This absolute value thing, this just means distance. This is the distance. Distance between an and 1. And they're saying the distances are getting close to 0. The distances are getting smaller, and that's why it's all fine. So I'm talking about the values getting close. They're talking about the distances getting smaller. Of course, it's all the same thing. You're right. I didn't mention that, but that's not the problem. Yeah? Does n have to be squared? No, n is just n over n plus 1. But there is something wrong with n. Yeah? It's true. So n is 1, 2, 3, 4. It's true n is not 0. 1, 2, 3, 4. And it's going on a whole bunch. It's supposed to go on forever, right? What is happening in the notes? Does it actually go on forever? Look, we happen to have it on a computer. Let's try to zoom in a little bit more. If you zoom in enough, you will see that actually the person who made the notes cheated, right? They were supposed to do all infinity many values of n, and they only did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. They only did 20 values of n. And because we can't zoom in, we can't see anymore. So the first 20 values are bunching up around here, but because it's paper, we can't physically zoom in enough. On Desmos, you can zoom in enough. So the paper version looks like this, and it looks fine. It looks like it's getting close to 1. On Desmos, we can zoom in, and that is why we're having a problem. In Desmos, we can zoom in a lot, and now we have an issue because we see that actually the numbers only go to 0.99, and they don't go to 1. OK? But of course, Desmos is a computer. Computers, paper cannot fit infinitely many things on it. On paper, we could only fit 20. On Desmos, we still can't fit in infinitely many. I only told the computer, please make n go from 1 to 100. And that is the problem. In Desmos right now, it is not plotting the infinite sequence. It is only giving you the first 100 terms. So why is it not going all the way to 1? The reason is it hasn't gone to 1 yet. Right? The limit is about where you get to when n goes to infinity. N is getting bigger and bigger and bigger. Right now, I've only gone up to 100. If I go up to 120, then I get a little bit more. 150, I get it more. 190, I get more. 200, I get even more. What if I go up to 1,000? Now I'm getting really close. What if I do 5,000? Aha! 5,000. Now I'm in the zone. So there we go. So the problem I had before was I didn't make n big enough. And limits are what happens when n is big enough, and how big can depend on the green zone. So before I didn't have a big enough n, now I do have a big enough n. Okay, but somebody comes up to me and they laugh at me and they go, okay, but what if I make it even smaller? Ha ha ha. They put, tricked you. Okay, that's fine, I can deal with that. All I gotta do is make n even bigger. So let's, instead of 50,000, let's do 9,000. Let's add some more zeros. Oh no, I killed the computer. Okay, 9. Eventually you're gonna kill the computer. That's too many. Okay, what about that many more? 9, 9, 9, 9, 9, 9. Okay, let's see. Let's zoom in and see. Did we make it in the zone? I think we're in. Okay, we got like a solid wall of orange made of stripes, and I think we're just barely in the zone. Okay. Can I do this? No, it dies. Okay, so even the computer cannot tell you for sure if the limit is equal to 1 or not, because the computer will eventually explode if you put a number that's too big into it. And it looks like Desmos explodes after 9,999 terms. You might need even more. Okay, so there you go. This is the problem. You need sort of infinitely many terms to see that it's getting closer and closer to 1. It's getting arbitrarily close to 1. Okay, so it's true, it's getting arbitrarily close to 1. But the reason is subtle, right? It's actually quite difficult in practice to verify. And we're going to see with algebra how you can do it. That's going to be next class. Okay, so the limit is 1. All of this to say, you could have put in that the limit is 1. The limit is 1. Whenever a sequence has a limit, we use the word convergent. So convergent is an adjective that means the sequence has a limit. Okay, so that's this example in the notes, exercise 144, seen both ways visually. And we've kind of done a little bit of a skip ahead here because I wanted to start with the graphical. I like pictures. So we started with the pictures, but actually the definition of a limit is all the way back in section 8.3, all the way over here. The section 8.3. So exercise 133 on page 307, this is the first example of a limit in the book. And this one is all algebra. So instead of doing it graphically first, they did it with algebra first. But I wanted you guys to see the graphical stuff first. But now let's do this one with algebra. So I'm going to fill in the values of n are here, and I'm going to fill in the values of an, which is a new sequence 1 plus 1 over n. Of course, you could do it in Desmos and see it visually, but let's do it algebraically. 1, when n equals 1, you get 1 plus 1 over 1, also known as 2. Maybe I'll wait for people in the back to quiet down. OK, 1 plus 1 over 1 is 2. When n is 10, you get 1 plus 1 over 10, also known as 1.1. 1.1, right? A tenth is a 0.1, so 1.1. What about n equals 100? 1 plus 1 over 100, you get 1.01. OK, what about 1,000? 1 plus 1 over 1,000, you get 1.001. What about 10,000? 1 plus 1 over 10,000 is 1.301. So the bigger n is, the closer an is getting to 1. It's always 1 plus a tiny bit, and that tiny bit is getting shrunk down from 0.1 to 0.1 to 0.01 and so on. It's getting closer and closer to 1. How do you measure if something is getting closer and closer? You measure the distance. And this term, an minus 1, this is the distance between an and 1. So if you put something in absolute value signs and you subtract them, the difference is, what is the difference between the two things? That could be positive or negative. If you take the absolute value, that gives you the actual distance between them. You might remember displacement versus distance. Displacement is like the difference. The absolute value is the distance. So let's do these numbers minus 1 and see what we get. So 2 minus 1 is 1. So the distance for the first number is 1. The distance from 1 for the second number is 0.1. The distance for the third number, 1.01 minus 1, is 0.01. So the numbers are getting really close to 1, and the distances are getting really close to 0. 1.001 minus 1 is 0.001. And 1.0001 minus 1 is 0.0001. So the numbers are getting 1 plus a bit. The distance to 1 is shrinking. It's getting really close to 0. We can fill in these boxes. So as n gets larger and larger, the distance to 1, the distance to 1 which is an minus 1, the difference between the number and 1 is getting smaller and smaller. So an gets closer and closer to the limit, a equals 1. So if the distance to something is going down to 0, then you're getting close to the thing. The quantity an minus 1 gets closer and closer to 0 as n approaches infinity. OK, so that is this little box. Same idea we've been talking about all lecture. The distances are getting very small. The numbers are getting close to 1. And this is what is called the definition of the limit. So the sequence is said to have a limit of a. And what does it mean for the limit to be a? It means that the distance, an minus a, can be made as small as we like. As small as we like is what I called before arbitrarily small. Arbitrarily small. Arbitrarily small. As small as you like. And here is the secret thing. By choosing n sufficiently large. So how big n has to be, it might have to be really big. It might be bigger than you can fit in your computer. But as long as you can make it as small as you like, when n is sufficiently large, big enough, then we say the limit is a. And we write this in two ways. One way is to say the limit as n goes to infinity of an equals a. This is option 1. Option 1. Or the other way we can write it is like this. This is a separate equivalent way to write it, like this. This is option 2. Option 2. Two ways to write the same thing. OK, that's the idea of a limit. The idea of a limit is going to be the big thing in the rest of the section on sequences, and it's going to be the same big thing again when we do functions and calculus later on. So it's really important you have a good understanding of what a limit is, which is why I tried to spend today just conceptually talking about it without any algebra to get in our way. Any questions or comments about what is the limit? What does the limit mean? This idea of arbitrarily small, arbitrarily close. That's what we're doing. OK, here is an example for you guys. So on the next page is exercise 134 and 135. These are extra videos, extra. It's already posted online. You can fill them in there. And exercise 135 has a corresponding example in section 8.4 with a picture. But these are extra. And the one I want you guys to do is all the way over here on exercise 137. It's the sequence 2 to the power n. So this is the sequence 2 to the power 1 is 2. 2 to the power 2 is 4. 2, 4, 8, 16, 32. It's this sequence, the doubling sequence. 2, 4, 8, 16, 32. And I want you guys to tell me what you think the limit is. What you think the limit is. And I have some options for you in Mathematize. Yeah. Here we go. 2, 4, 8, 16. The limit is what? The limit is what? And I'll give you 2 minutes to do this. OK, who needs more time? It looks like we're pretty stabilized here, around 60 people. Who is still going? Who needs more time? One or two people. OK, I'm going to speed this up. I'm going to give the 1 or 2 people, I will give you 15 seconds to pick a guess. And it's multiple choice. It's OK if you get it wrong. Just take a guess, whatever you think the answer will be. And we're going to go from there. Okay, let's take a look at what people said. So I'm going to reveal who said what. Okay, out of 68 people, 23 people said the limit does not exist. 54 people, a huge majority, said the limit is plus infinity. These other options were not very popular. Let me explain what these two things are. So far in the class, I have said what it means for the limit to exist and be equal to a, right? Some number. It means you're getting very, very close to that number. So let's review what these two things mean. The second one in particular is new. So let's see what it is. So the limit does not exist. The limit does not exist. If the limit existing means that you're getting very, very close to a, what does the limit does not exist mean? Means you are not getting close to a. I'm going to call it L for limit. So before we said, what does it mean for the limit to be equal to L? Like L was 1 or 0, you're getting really, really close to 1 or 0. What I've written down, you're not getting close to L, that means the limit is not L. The limit does not exist means the limit is not L for any value of L. For any value of L. Okay? So the limit does not exist means you're not getting close to any single number. What does the limit equal infinity mean? The limit is plus infinity means what? So the limit being L means you get really close to L. What does the limit being plus infinity mean? It means you get close to infinity. What does close to infinity mean? It means you are bigger than any number. So you become what I call arbitrarily large. Arbitrarily large. So the limit is plus infinity means you get close to infinity. I'll show you what this looks like on Desmos. So let's take this thing. Let's go back to the first 100 terms. And let me do the sequence, which is the sequence 2 to the n. This is the sequence we care about right now. 2 to the power n. And so what is the sequence doing? There's 2, 4, 8, 16, 32. This sequence, it's becoming arbitrarily large. The numbers get bigger and bigger forever. So if I was going to draw the space y greater than m, and I add a slider, x greater than m, and I draw a slider for m, then eventually you're in this red zone. No matter how big someone says make the number, if someone says, I want you to be 1,000 big, I just scroll over, and eventually the numbers are bigger than 1,000. This is arbitrarily large. That means the limit is plus infinity. But hold on. What's the right answer? The right answer is actually both. The right answer is both. Both are correct. If on a test you select 1 out of 2 of them, then you don't get the full marks. Why is it both? Because it is true that the sequence, they are getting arbitrarily large, but are they getting close to any individual number? Also no. So the limit does not exist. So it's both does not exist and plus infinity. So both of these are correct. And I probably for sure will actually have one like this on midterm 2, where it says select all that apply, infinity is an option, does not exist as an option, and you have to select both to get the right answer. Okay, we're going to do more limits on Wednesday and Friday and probably for the rest of the course. So keep an eye on that.